Welcome to all of you. In this lecture, we are going to have a continuation of linear convolution by using frequency domain method. Let us first go through the various steps involved in this frequency domain solution of linear convolution. Given the sequences x of n and h of n, step 1. Calculate the output sequence length n is equal to length of x of n plus length of h of n minus 1. Step 2. Make up the length of x of n to n by inserting zeros at the end. Step 3. Make up the length of h of n to n by inserting zeros at the end. And step 4. Apply n point DFT to x of n to get x of k. Step 5. Apply n point DFT to h of n to get h of k. Step 6. Multiply x of k and h of k to obtain y of k. The last step. Apply IDFT to y of k to obtain y of m. Now, the sequence y of m is of the length capital letter N and is the result of linear convolution of the sequences x of n and h of n. Now, let us go through a problem where we are going to make a follow-up of all these steps to calculate linear convolution in frequency domain. The problem statement. Find the linear convolution of the sequence x of n is equal to 1, 2 and the system having the impulse response h of n is equal to 3, 4, 5. So in each of these two sequences origin is mentioned. So throughout the process of calculation we are not going to consider the origin for any criteria. Only once we have got the output sequence, that is final y of m, there in order to mention the origin we are going to consider the positions. Let us go through the solution. Now given the sequences x of n and h of n, first identify the length of each of these sequences. So length of x of n is equal to 2, length of h of n is equal to 3. Going through the steps. Step 1. Calculate the output sequence length given by capital letter N is equal to length of x of n plus length of h of n minus 1, that is 2 plus 3 minus 1, that is equal to 4. Step 2. Make up the length of x of n to n by inserting zeros at the end. So length capital letter N is equal to 4. X of n is having two elements. Therefore, two zeros has to be inserted at the end so that the sequence length x of n become equal to 4. So that has been done over here. Next step, make up the length of h of n to n by inserting zeros at the end. Now h of n is having three values given. We have to insert one zero so that the sequence length h of n become equal to 4. And that has been done over here. Now in the next step, apply n point DFT to x of n to get x of k. So in the input we are having 4 values, therefore we can make use of the matrix method of DFT to calculate x of k, and that has been done over here. So to the factor values, the x of 0 to x of 3, that has been substituted over here, and after simplification this is what the answer we have got. So x of k is equal to 3, 1 minus 2j minus 1, 1 plus 2j. The next step, apply n point DFT to h of n to get h of k. So h of n is also having 4 values. Therefore, we can again go with the matrix method of solution, and that has been done over here. And we have got h of k as 12 minus 2 minus 4j, 4 minus 2 plus 4j. The next step, multiply x of k and h of k to obtain y of k. So this is x of k and this is h of k. We are going to multiply them position by position, or we can say the dot product. So after multiplication we are going to get this answer. So 36 minus 10 minus 4 minus 10. The next step, apply inverse DFT to y of k to obtain y of m. So for these values, we are applying the inverse DFT again using the matrix method. So that has been done over here. Substitution has been done, and after simplification, we are going to get the answer as 3, 10, 13 and 10. So finally, y of m is represented as 3, 10, 13 and 10. So once we got the answer at this stage, then we need to identify which is the origin. So for that, we are going to identify the position of the first element by using this formula, that is x underscore si plus h underscore si. That will be equal to, with respect to this particular problem, x underscore si is minus 1, h underscore si is minus 1. So adding these two, we get minus 2. Therefore, position of the very first element in y of m is equal to minus 2. So this is minus 2, minus 1 and this is 0. Therefore, this is the origin. So two things I need to mention over here. The first thing is, we need to remember that convolution in time domain is equal to multiplication in frequency domain. So that's why at this particular stage, we are going to say multiply x of k and h of k, because we are doing the convolution in time domain. So that will be equivalent to multiplication in frequency domain, that is being followed. The second thing is with respect to the notation. So throughout the linear convolution, I am going to represent the output as y of m. So this y of m is being used just to avoid all kinds of confusion. In most of the context, we can simply say it as y of n also. So y of n also we can say, but to avoid the confusion, for all reasons, I'm just making use of y of m term. Thanks for joining.